The neuron is represented by a circle. The input arrows show the signals coming into the neuron. We then visualize the weighted sum of these inputs. Next, the sum is processed through an activation function, indicated by an arrow. When using the ReLU activation function, we can see the ReLU equation and understand how the neuron fires. Finally, if the neuron fires, the output signal is generated and sent out. The ReLU graph shows how the ReLU activation function works. It's a piecewise function that outputs 0 for any negative input and passes positive inputs as they are. This helps the neural network by allowing only the most significant positive signals to pass through, effectively ignoring negative noise. The graph has a flat line at 0 for all negative values and a straight line with a slope of 1 for positive values, making it simple yet powerful for deep learning tasks. How ReLU is used in recognizing handwritten digits. Layer-by-layer processing. When a neural network processes an image of a handwritten digit, each layer in the network applies the ReLU function to the output of the previous layer. This process helps in preserving positive signals, which are important features, and ignoring the negative ones. When building a neural network to recognize handwritten digits, each neuron in the network focuses on processing a small part of the image, such as detecting edges or shapes. It sums up the input signals it receives, and then the activation function determines if the neuron should fire and transmit its signal to the next layer. For example, if you use the ReLU activation function, only strong signals, positive numbers, are passed on, while weaker signals, negative numbers, are ignored. This selective process allows the network to concentrate on the most critical features, like the curve of a 9, enabling it to accurately classify the digit.